So now we're going to go over some basic electrical components, and what they look like, some basic handling precautions. One thing that you may have heard of and you may have seen is these little anti-static wristbands, or actually that's what these mats are. These are ESD mats. That's electrostatic discharge. That's also what that blue one is back there. We're in Louisiana. It's very humid here in Louisiana, which usually means you can't really build up much of a static charge unless it's like the winter and the heaters are going full blast and you're wearing a wool sweater. So you do take, you don't want to be completely, like, oh, it doesn't matter. But honestly, it's pretty rare here in Louisiana to damage. And also most of the components we give you are not sensitive to electrostatic discharge. So it's not something to be overly concerned about. All right, so we're going to cover, sort of the basic building blocks, which are resistors, capacitors, inductors. And then we're going to talk about a few different semiconductors, diodes, transistors, and we'll just touch on some integrated circuits eventually. So resistors, this is the classic first component that everybody deals with. So this is just a thing that has a specific resistance that you want that resistance to be in the circuit, right? So like we said, that's ohms are the unit of resistance, and it's pretty common to see kilo ohm and mega ohm resistors. The most common style of resistor uses a little color code to tell you the resistance. So this is a little bit, actually, can you hit the light? It's a little bit hard to see here, but that's black, brown, red, orange, yellow, green, blue, violet, gray, and then white. So you'll see this band pattern on the resistor, and that will actually, because these are usually too small to print the actual number on, so that will tell you what the value of the resistance is. And there's all kinds of mnemonics for remembering that. So black is 0, and then brown is 1, red is 2, orange is 3, yellow is 4, green is 5, blue is 6, purple is 7, gray is 8, and then 9 is white, right? So that is used both for digits and a power of 10 multiplier, right? So for example, that's blue, right? So that's 6, and then red, that's 2, so 6, 2 times 10 to the 2, right? So that's 6,200 ohms. And then there will usually be a band that is a tolerance marking, right? So these things are not going to be exactly whatever the value they are. They're going to be designed to be manufactured to something close to that value within 5%, 10%, etc. So that's what this tolerance band is. The most common values you'll see for that are gold for 5% and silver for 10%. So like I said previously, resistance, I squared R, you're turning electrical energy into heat. And usually that means the bigger the component is, a resistor isn't doing anything other than turning that energy into heat, right? So they're going to be rated for a particular power rating. So these are going to be in watts. Quarter watt and eighth watt are what the typical resistor values are until you start getting into like a high power resistor. And once you get into those greater than 1 watt resistors, those are usually going to be like have some sort of heat dissipation. Maybe they're a big chunk of ceramic instead of one of these little pieces of plastic, or they may have like a little metal housing with some fins on it to disperse heat. So those are basically ways going to be made out of materials where they're not just going to melt super quickly, or they have ways to dissipate that heat, right? These things are really just wire or stacks of carbon to give a particular value of resistance. So that's why you usually, if you need a lot of energy dissipated, you have to start building them both larger and build some stuff on it to handle the heat. So like we talked about in the last lecture, resistance doesn't have direction, right? So it doesn't matter which way you install it, right? Because you will have, there's two leads, and the resistance is between the two leads, but it doesn't matter. So you don't have to worry about, oh, I need to have the tolerance marking this way or something like that, right? Like I said, because these things are basically just chunks of carbon or wire wound up, you don't, if you give them a little zap because you were rubbing your feet on the carpet, that's not going to hurt them at all, right? So you don't have to worry about ESD precautions with these things. What usually will happen is if you're moving, particularly if you're prototyping something on a breadboard or you're moving it around a bunch, you keep bending the leads over and over again, and you'll just bend the leads over and over again and again and again, and eventually they'll just break, right? Because they're just little pieces of metal. So you want to try and make sure you're not like, you can bend them to get the holes through the circuit board you're trying to solder or to push them into the breadboard, but try and minimize bending them over and over again so you don't break it. But if you do, resistors are usually pretty easy. We have a lot of spare parts. So next thing, basic component is called a capacitor. All right. So the units for this are farads, which is what this F is. But a farad is a coulomb per volt, and a coulomb is a lot of charge. So usually you don't see farad capacitors or even millifarad capacitors unless you're digging into like some power electronics or breaking open a microwave, right? The kind of capacitors you guys are going to deal with in this are going to be picofarad or microfarad. So these are going to be relatively small. And what these components do is you are storing energy by creating an electrical field. So that's why you have this little symbol with two plates. So the simplest capacitor is two plates that you separate, and you apply a voltage to that, and that'll charge up one plate, and it'll push the opposite charge across, not through. Current can't actually, well, charges cannot actually flow from one side to the other. But because the charges you build up on one side repel the other, it will allow current flow until you build up so much charge that you can't push it further. So those are usually gonna just have the number written on them. Some of the smaller ones use a like 3-digit code that works similar to the resistor code, where it's digit power of 10. But usually those are using a base value of like picofarads, because if you're talking about something small enough where they need to use that code, that also means it's going to be a small capacitance. One tricky thing with these is that some of them are polarized and some of them are not. So if they are polarized, the schematic symbol will have a marking like this, either a plus sign to indicate a positive sign, but also this curved plate that indicates the negative lead, or the negative side of the capacitor, right? So this is actually a polarized capacitor, even though it doesn't have a plus or minus sign on there. This is the negative side. If they are polarized, they are going to have a marking, and that will usually mark the negative lead. So On the larger ones, it will have a like negative sign and an arrow physically pointing to that. But if you're talking about a small surface mount, it may just have a stripe on one side that indicates the negative symbol. So here's a bunch of pictures. So this is one of those ones with like the number codes that we were talking about. These two on the bottom here, these are two polarized examples. So you can see there's a negative sign in this band here. And like this is the one that has a negative sign and the arrow pointing this way. So that indicates this is your negative lead. You can see this one has a little positive sign. These are pretty uncommon to see, but here's one of those ones where it just has a stripe to indicate the negative. So these are all basically like the same thing where I said when you fundamentally get down to it, it's a couple of plates that are separated by something that's called your dielectric. But because the way that capacitance works, you want a very small gap, but a really large area. So what you'll actually see is if you were to crack one of these open is there's a big foil thing that's wrapped around and you have the dielectric sandwich between the two electrodes. So this is just sort of reiterating that the physical size will tell you what is the max voltage they can handle. So at a certain point, if you get the voltage difference across the two plates too large, you can actually make charges start to jump across the gap. That's called a voltage breakdown. So these are all going to be rated for some maximum working voltage. Basically, here's the largest voltage you can apply to the capacitor without it no longer functioning as a capacitor, right? That is sometimes going to permanently damage the capacitor and sometimes it won't. It depends on, what it's made out of. Usually you don't talk too much about the temperature changing the actual capacitance. Like if the capacitor gets really hot or really cold, you usually don't worry that it's going to affect, but that is not true for all materials. And if you change the temperature enough, any of these fundamental quantities is going to change, right? But usually if you're talking about like room temperature changes, that you're not too worried about the design capacitance changing. Like we said, a lot of these are not polarized, so you can put it in either way. There are going to be some, so electrolytic capacitors, like these two right here, those do have the polarity markings, and you need to install them properly. Usually those particular ones, if you install them backwards, they are that's usually gonna permanently damage the capacitor and you have to basically replace it with a new one. Like I said, you usually don't have to worry about ESD with these. Again, they're sort of designed to hold charge. And like all of these components, if you bend the leads over and over again, you'll break it. A somewhat less common component is an inductor. But if you are trying to do some sort of frequency-based or time-varying circuit, you may run into an inductor. So in these cases, what you're actually doing, instead of building up an electrical field, you're building up a magnetic field, so the current goes through these. So that's why they are usually some sort of wire coil, either just a coil sticking up in the air, or it may be wrapped around like an iron core to give you a better inductance, right? So in those cases, the iron or the open air, that's sort of the equivalent of the dielectric in the capacitor, where you're building up a magnetic field. And then a lot of times you will have what is effectively two inductors that are wound around a common core, where you're using the magnetic field to transfer energy from this coil to this coil. And that's it. That's what a transformer is, right? And usually what you're doing there is you're changing, a low voltage to a high voltage, or a high voltage to a low voltage. When you have an inductor by itself, what you're actually, you're like I said, you're more interested in storing energy within this magnetic field for some purpose. If you have a big one in particular, and sorry, I sort of glossed over this. The units for these are henries. So millihenries and microhenries are what you're probably going to see. A Henry capacitor is going to be a big chunk of iron with a big wire like this kind of thing. One thing that you want to watch out for, there is a style of inductor like this seafoam green kind of color up here, that they pretty much look like resistors, except they're like blue or blue-green. And the confusing thing about these is, because they're a big long coil of wire in there, is they will not have like a zero resistance. So I personally try to avoid these, and I've tried to get any random ones that we've had out of the lab. Just that's something to be aware of. If you're like, why does this, if I measure the resistance of this, what I think is a resistor, does it have a very different value? And usually that means it's because it's actually an inductor, and these will use the same color code as the resistors, except it'll be telling you the inductance in amps, right? So because this is something depending on the physical geometry, right? You need bigger wire, you need a larger coil to get a higher inductance, or a more henries. So that physical size is going to tell you like how much is how big of an inductance it has, right? Most solid materials are going to have less temperature dependence, or have more temperature dependence on their inductance, because there's actual material there to be heated and cooled, whereas air is, it's just the gas is not particularly contributing to the inductance. So the changes in the air temperature are not really going to cause that inductor value to change. Again, like resistors, since these are basically just a coil of wire, they are not going to have a polarity. You can always send the current flow the opposite way. And because these are made out of relatively robust, simple materials, you don't have to worry about ESD. Again, if you keep bending them over and over again, you can break them. What you do have to usually worry about is, now if you've started like I said, you're usually trying to do some sort of time dependence, frequency dependent thing with these. So that frequency, because these are going to create changing magnetic fields that are going to interact and propagate through the air. It depends on if they're close to other wires, you can get strange effects. So usually you want these to be relatively rigidly mounted so they can't move around, because as they move close to or away from other circuit components, you can get effects that are probably undesired. All right. So that sort of covers the basic, what are typically called passive components, resistors, inductors, and capacitors, because they just sort of react to the voltage that is applied to them. They follow Ohm's law. And if once you learn the magnetic field and electric field equations, they follow those basic equations, right? Now we're going to start talking about what we call semiconductors, and these are components that don't follow Ohm's law, and they depend on the submolecular properties of the things these are actually made out of. These are, going to be made out of silicon doped with some other sorts of materials, right? Diodes are the simplest version of these components. We usually consider them passive because they don't, you can't build an amplifier out of just some diodes, right? So you have a positive and a negative sign of a diode. It's called an anode and a cathode. And the reason you have this triangle symbol is basically the simplest thing you can do with the diode is to use it as a directional limit to the current. So current will be able to flow from the anode to the cathode, but it won't easily be able to flow the opposite direction. If since we have a whole lot of mechanical engineers in here, these are basically electrical check valves, if you know what a check valve is, right? So current can go this way, but it cannot easily go the opposite way. So usually what you care about here is how big of a voltage change you see across the diode, and that's going to depend on the actual semiconductor material it's made out of. So that's why these will be referred to by that, element, usually silicon, germanium, gallium. Those are the common source of things. So this is a signal diode. This is a silicon diode, as is this one here. There are also diodes that give off light. That's what an LED is. It is a light emitting diode. That is what these little arrows coming off of the diode symbol on the left here. That is, that's the light coming out. So that's what the symbol for an LED is. So there's a few important different numbers. So like diodes are not simple like a resistor, where like a resistor really only has the one number you need to know. It's the resistance. So you have what is called peak inverse voltage. So that is basically, like I said, current can't flow through back easily. But if I apply a large enough voltage in the backwards direction, you can force current to flow in the opposite direction. And that's what the peak inverse voltage is. They will also have a maximum amount of current that can flow through them before you start to basically heat up the diode and damage it. That's called the maximum forward current. And the maximum forward voltage drop, that will be the voltage drop that you see at that maximum current. And then if you are below this peak inverse voltage, but you are applying basically backwards voltage, there is a little bit of current that can actually get through. And that's what this reverse leakage current is called. So this IR symbol usually. So, but that is typically like on the microamps. So this is, if you're dealing with a milliamp circuit, you can usually say, oh, that's effectively zero, but that is a spec that you'll see, and it is something to be aware of when you're handling diodes. So these are the first semiconductor things that we're talking about. And these are the things where we're worried about giving them a shock with static electricity. Like I said, because the air is so humid here, that's really not a practical concern most of the time. So you don't need to wear one of these wristbands when you're handling these, just because it's very unlikely. Also, most of them have a protective housing on it, so yes. So technically, these can be damaged with ESD, but in practical terms, it's not something you need to be concerned about. So, and then we have a whole bunch of things that are basically just allowing current to flow in different situations, different directions. These are connectors, switches, and plugs. These don't really do anything different than a wire does, other than they're designed for you to, change them, unplug them, switch them. So, so you may see a few different multi conductor plugs. So this is, you know, what I would call a headphone jack, but is technically a 1/8 inch stereo plug. So this is actually three different contacts here. This is actually the proper name for this is a sleeve ring tip. So, you know, you have a sleeve, a ring, and a tip. And if you were to cut open the cable that was behind this, you would see three different wires that are connected. And if you broke open this plastic, you can see where it is connected to these each individual contacts. This is an RCA plug that's an older style connection that's for two different things. And this is basically the same thing as this stereo plug, except there's only two contacts instead of three. And the reason this is called stereo, right? Stereo means like right and left audio. So in this case, you would have like a right channel, a left channel, and a ground. So the other, you know, active or semiconductor components that you see are what you call active components. So those are going to be transistors, which is sort of the most basic semiconductor or the most basic active component. And then, you know, integrated circuits are where you get after that. And these are specific chips that are designed to do a, you know, they are built for a specific purpose, unlike the transistors, resistors, diodes, where those are sort of base level parts that you build everything out. Transistors, you will see a bipolar. Basically, there's two different ways of building this. You can build them out of two silicon diodes. Those are called bipolar transistors, or you can build them out of metal oxides, and those use something called the field effect. So this is you may say something called a MOSFET. That's a metal oxide. Don't remember what the S stands for. Field effect transistor. FET is a field effect transistor. And then so integrated circuits are just basically all modern electronics. They're chips designed in a fab to do a specific thing, and they can do all kinds of different things. So transistor, this is your basic thing. So these are all symbols for different styles of transistors. But the important thing is that they're going to have these three leads, right? And then this is like basically 1950s Nobel Prize, you know, first transistor type. I don't think this is the actual first transistor, but this is like what are now basically there's thousands of these, millions of these built into a single chip these days, right? So you can see the three leads. I can get that out. So one lead, two lead, and then the third lead is actually back there. You can see the wire kind of coming back up. So these vertical square lines, those are the field effect. Those are the FETs. And then these are your bipolar or your silicon transistors. They're going to use this style of symbol. Okay. For whatever reason, they decided to give the leads different names for the two styles of transistors. So you have collector, base, and emitter for the bipolar transistors, and then you have the drain, gate, and source for the field effect transistors. Sometimes you can easily spot the difference between them. So it usually, if there's a big, you know, piece of metal on the back here, that's actually a heat sink. That's going to be a field effect transistor. A lot of times these smaller ones are the bipolar, but you will sometimes see field effect transistors in these smaller packages. The important thing here is there's going to be a stamped on, printed on part number label that's going to tell you what it is. And you usually have to pull up the data sheet to see which pins are which, right? Because they usually won't be labeled with like a B, C, E, or a D, G, or S. So you usually have to open up the data sheet and figure out which pin is which. So because these pins all do different things, that means pretty obviously that they're polarized and you have to put them in the right way. Those bijunction transistors, those are, use the same technology as the diodes, which means they can be damaged by a static shock. The field effect transistors are probably the thing where you're most likely to actually damage one of these. At least in the fall, you're not gonna handle any of these, so that's not something you really need to worry about. But yep. And always you can just physically break that. These things are not designed to hold weight or be bent over and over again. Okay. So integrated circuits are basically everything else, and at this point in technology is basically, this is all of modern electronics is integrated circuits. So what they're going to have is they're going to have a whole bunch of pins, and they're going to do all kinds of different things. So these are going to be the sort of thing where if you don't have the data sheet, which is basically the manual that tells you what this does and how it works, you're not going to know how to do anything with it. So this is what we call a through-hole package. This is sort of the largest. This is called a dip package. So this is what you'll first encounter, and there will be a marking. Either you can see kind of here, there's a little dimple there. There will be a notch on one side often, and what those tell you is the orientation. So the dimple will indicate pin 1, and the notch will basically say, if you point the notch up, the pin on the upper left will be pin 1. And then pins are numbered descending down one side. So you go 1, 2, 3, 4, 5, 6, 7, and then you go up the opposite side. So you go counterclockwise around. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, right? So, and then, like I said, the notch tells you the which end pin 1 is on, and these are going to be stamped with what is usually the first chunk of numbers is the actually part number, and then there will be a letter that is like a package code, because a lot of times you can find the same part in a bunch of different shapes and sizes. And then usually this second stuff here, that is like manufacturing codes, where if Motorola builds a batch of bad chips, they want to be able to track down, these were all the ones that came out together. So those are not something you have to worry about. But sometimes there may be like special like options or stuff in the first few digits. A lot of times what you end up doing is, hey, let me just type these numbers into Google and then start deleting from the end to figure out where the actual I usually you can sort of grab like the first line and that'll tell you, but sometimes you have to include some of these other numbers, or you have to delete some of these the last couple of numbers, because that's a specific option. So obviously, if you have different number of pins that do different things, it matters which way you put it in. Again, these are more complex. These are built out of the other semiconductors, so they are going to be susceptible to ESD. The other thing you really want to be careful about is not bending these small pins. So you're going to be installing these either directly into a circuit board or into a socket. And in particular, if you're using one of the, so you can see the sockets here, those are things that you actually solder in, and they hold the chip so that when you break the chip, you can just pop the chip out and put a new one in without having to desolder it. But when you do that, when you install the chips in there, it can be easy to kind of have the chip cocked, and those pins are pretty small, so they're easy to bend or improperly install or break off. So like I said, if you're handling something ESD, you want to take a few basic precautions. So work on an anti-static mat. Most tools like a soldering iron are going to be grounded just as part of their power supply. And if it's something where you're really worried, you want to wear one of these ankle straps, or wrist straps. But you'll notice there is a clip on the end here. If you don't clip this onto either an ESD or like a ground pin of a power supply, this doesn't really do anything. Because all this is a, like couple kilo ohm resistor that you connect to ground. So as you work, right, any charge that builds up can just trickle through the wire and into the ground and spread out, so you don't build up a shock. So the sort of the thing we're going to use when we start working with components is what's called a solderless breadboard. So these are things where you can build prototype circuits, right? So they have this particular hole pattern so that you can just put components into them, and there are some pre-existing connections underneath this board so that you don't have to basically wire everything individually together, right? And these will have a consistent connection pattern that we're going to go over now. So typically what you have is rows across the top and bottom that are connected to each other. So this entire row is connected to all of the other holes on the roll. And then this separate one is the one right below it is not connected to the one above it. It's so you have another parallel set. And usually you use this one on the top and this set on the bottom for power, right? So my personal practice, what I like to do, if I only have one voltage that I'm working with, I do the positive voltage on the top and the negative voltage on the bottom, and then allows me to keep track of, okay, power generally flows from top to bottom. If you have more than one voltage, so you may have like a 5-volt portion of the circuit and 3.3-volt portion of the circuit, that's where why you usually have like two sets here, where you would have like, okay, let me do the 5 volts up here, the 3.3 volts up here, right? But that's got a negative on each one of those and a positive on each one of those, right? Then typically this middle portion here, that's where you're building your circuit, and there's this central divider here. Okay, each of these columns is all of the column is connected to each other. So you typically connect one lead here, and then you move it somewhere to the left or right of it. Because if you just connect a component from here to here, you just have a short circuit around that component, so it probably isn't going to do anything. And then this center strip is sized so that you can put your integrated circuits across this, and then have the pins connect to separate columns, right? So something else that is in your kit and is useful for working with these breadboards is you should have a set of jumper wires here. These are also going to use a color code like the resistors. Typically they will be colored, the wire will be colored to match the number of spaces on the breadboard. So for example, the little orange wire will move 3 spaces over. That can be useful. I mean, you can always just grab and see if it fits, but it's useful to be able to be like, oh, I need to move 2 spaces. Let me grab a red jumper. And then there is in the orange and yellow and red, there's usually a longer set as well as the short set. And I honestly don't remember what the color usually when you're grabbing these really long ones, you're just like, I just need a long wire to go from here to here, then a specific number. The other key thing when you're working with these, if you may need to just grab some wire to make jumpers, but you don't want to use stranded wire. You want to use solid core wire, and I'll show you some examples after this, because you have to push the wire into the hole, and if it's stranded wire, it's usually just going to bend over when you try and push it in. Whereas if you use solid core means that the wire, the inside of the wire is a single big conductor, so it'll be stiff enough where you can actually push it into the breadboard. If you don't have solid core wire, what one trick you can do is basically you take a little bit of solder and you solder, you add solder to the end of the wire, because the solder, once it cools down, will be stiff. And then you can usually push it in. But even then, sometimes it can be a little bit tricky, because also you have to make the solder small enough that it can actually fit through the hole, but still get enough on there where it'll actually reinforce. All right. You guys have any questions about any of that?